All right, in this section, we're going to look at finding moments, centers of mass, and centroids, and we're going to build up to it. So in this one-dimensional system, we have some isolated masses, M1, M2, M3, and so on, located at these positions. And we imagine, like, let's say the fulcrum here is at position 0, so these xi values are like their coordinates, so they're just distance from the origin, and they're a directed distance too. And the moment about the origin is given by this sum. You just take each mass, multiply it by its position, its x-coordinate, and then add up those products. The center of mass in this system we get by taking the moment about the origin and dividing it by the total mass, and the total mass is just the sum of all of the masses. So now consider a two-dimensional system. And again, we're looking at isolated masses. Right, so we have, in this case, we could see we've got M1 at this position here, X1, Y1, and M2 is up here, and Mn is down here in the fourth quadrant. In order to find the center of mass, we need to find the x-coordinate and y-coordinate for the center of mass. So we're going to find two moments. The moment about the y-axis is given by this sum, each mass multiplied by its x position. And the moment about the x-axis is given by each mass multiplied by its y position, and we add those up. We get the coordinates for the center of mass by finding these fractions, right? So the x-coordinate is given by the moment about the y-axis divided by m, and the y-coordinate is given by the moment about the x-axis divided by m. And again, m is just the total mass of the system, where we just add up all of those masses. So an example here, suppose we have these four masses and at these positions. So we could sort of, they're listed here in the problem, they're also given here in the figure. The figure could look a little bit confusing near the origin. So M2 is a mass of 3, and that's located at 0, 0. M4 has a mass of 9, and that's located at 4, 2. And then, of course, we have M3 over here and M1 down here. So M is the total mass. And we just find it by adding up the masses. So that's 6, M2 is 3, M3 is 2, and M4 is 9. And that gives us a total mass of 20. And now we're going to find the moment about each axis. So the moment about the y-axis is given by a sum, and we're going to add up. So I'm going to use some summation notation here, this capital sigma, where it says add up what follows. And so I'm going to just take these products of mi times xi. That means each mass by its respective x position, and then we're going to add those up. So m1 x1 is 6 times 3, so that's this mass times its x position, and then m2 x2, m3 x3, m4 x4. And if you add up these products, you'll get 44. So there's the moment about the y-axis. Moment about the x-axis is given by this other sum. You take each mass, multiply by its y-coordinate. And so just going up here in the figure again, we've got 6 times -2 plus 3 times 0 plus 2 times 3 plus 9 times 2. And if we add up those products, we'll get 12. Now we just take these three values that we found, the mass and each of the two moments. We use those to find the center of mass. So x bar is my over m. That is 44 over 20, or 11/5. And y bar is mx over m, so that is 12 over 20, and that is 3/5. So that means that the center of mass is this point here, 11/5, 3/5. So, you know, looking at what we've done so far, you know, this is a section in a chapter called Applications of Integration, and it seems like we haven't done much integration yet. But whenever we say, you know, whenever we approach a problem by saying we're going to add up a bunch of stuff, we know that a definite integral is not going to be that far behind. You know, the definite integral is just our magic adding machine. And I'll just note that the scenario that we're in right now isn't exactly like real world scenario, in that, like, we don't encounter isolated masses, right? Usually we have a mass of something with some kind of continuous surface. And that's where we're headed after this, is looking at those. We call it a planar lamina, and we'll actually need calculus to find the center of mass in that situation. So here is, in this figure, this is sort of what we imagine like a planar lamina to be, and we're going to imagine that it is like a two-dimensional figure of like uniform thickness and uniform density. So there's not like, it's not like heavier stuff on material on one part of it, or it's not thicker on one end than it is on the other. So we're still making a bit of a simplifying assumption here. But we're going to see how what we did in the last example kind of build to these integral formulas that we have here. So this planar lamina has a mass, and we're going to find the center of mass. So the way we do it is we draw a sample rectangle, like we do so much of our applications. You know, we're going to just look at a sample rectangle, see, can we find the center of mass for that rectangle? So the sample rectangle has an area, and since it is uniform density, rho, that's this Greek letter here, is called rho, R-H-O. The mass of that rectangle is just going to be the area times the density. So our mass of this is rho times the area. So the area is the vertical distance, top minus bottom, times the delta x. The f function's on top, so I'll have f of x sub I minus g of x sub I times delta x. All right, so again, we're looking at this planar lamina from A to B, and we imagine that we're just stopping at this arbitrary x coordinate, which we're calling x sub I in this figure. And now we're going to consider this mass, the whole mass, the entire mass of the rectangle, to be located at its center. That's a reasonable assumption to make. This is all of uniform density and uniform thickness, and a rectangle is symmetric. So, you know, it's fair to consider the mass just to be located at the center. Okay. Now, let's get the coordinates. So the y-coordinate will be the distance from the x-axis, and the distance from the x-axis is going to be given by, you just take the average of the f of x sub I and g of x sub I. So we'll add those up and divide by 2. So there's distance from x-axis. And then the distance from the y-axis, well, that's just x sub I. That's just the x-coordinate. So the moments about the x and y axes are given by these two integral formulas. The moment about the x-axis is given by, we're just going to add up the mass times the distance from the x-axis. So the mass is this part here, right? The density times the area gives us the mass of that rectangle. And then this right here is the distance from the x-axis. Similarly, the moment about the y-axis is given by the mass times the distance from the y-axis. So here's the mass part, rho times the area, and then its distance from the y-axis is just plain old x. So that's where these integral formulas come from. You don't have to memorize these formulas. You know, they'll be provided for you, but you do need to know when they're used, right? You do need to know that, oh, if I'm looking to do a center of mass problem, these are the integrals that I'll need. So, and then we find the actual center of mass using the same formulas as we did in the last example. You just take the moment about the y over the total mass to get the x-coordinate. You take the moment about the x-axis over the total mass to get the y-coordinate. And then I guess I have a little bit of a bad line break here. At the end, m equals just rho times the area. That gives us the area of the whole planar lamina. So let's do an example. In example 321 here, we want to find the center of mass of the lamina of uniform density rho, bounded by the graph of f of x equals 4 minus x squared and the x-axis. So, you know, I guess the x-axis would be g of x equals 0. And this is a fairly simple figure to draw. Alright, so our f of x is the function 4 minus x squared, so that's just the downward opening parabola starting up at 4. It'll cross the x-axis at 2 and negative 2. So, and then of course there's y equals 0 at the bottom. So there's our planar lamina. Now, we want to find the center of mass. You know, the first thing we'll do is just, I guess, I would take advantage of some symmetry here, right? This figure, this region is symmetric about the y-axis. So we know that x bar is going to be 0. So we know x bar is equal to 0, which means we don't need to do the integral for the moment about the y-axis. We do need to do the integrals for mass and for the moment about the x-axis. So let's see, the mass is rho times the integral. The x bounds of this region are from -2 to 2. And the length of, if we draw a little sample rectangle here, f minus g is 4 minus x squared minus 0, so just 4 minus x squared with respect to x. And let's integrate. So it's just a power rule. It's a nice polynomial. So 4x minus 1/3 x cubed from -2 to 2. And plugging in the upper limit, 4 times 2 is 8, minus 8/3, minus, and then if we plug in -2, that'll be a -8 plus 8/3. So that's really just 8 minus 8/3 times 2, I think, if you chase the signs through there. And I get 32/3, so this mass is 32 rho over 3. The other integral that we need to do is the moment about the x-axis, and I'm going to just scroll up here. So that moment is given by rho times the integral. Our limits are from -2 to 2. Now f plus g, because g is 0, f plus g is the same as f minus g, so we're going to have f plus g over 2, so that's just 4 minus x squared over 2 times f minus g times 4 minus x squared with respect to x. I'm going to pull out that factor of a half. Here I'm going to take that out, so we'll have rho over 2 outside. And then I'm going to FOIL out this product. I'm going to multiply 4 minus x squared times 4 minus x squared. And that's going to give me 16 minus 8x squared plus x to the 4th. And another polynomial, so let's integrate. We get 16x minus 8/3 x cubed plus 1/5 x to the 5th from -2 to 2. And let's plug in our limits. So when I plug in +2, 16 times 2 is 32, minus 2 cubed is 8, and 8 times 8/3 is 64/3, plus 2 to the 5th is 32 fifths. And then we'll plug in -2. With -2, we're going to get all the same values. They're just all going to be negatives because these are all odd powers on x. So we have a minus 32 plus 64/3 minus 32 fifths. So this is rho over 2 times, and again you'll notice I just have the same values here, right? If I chase the signs through, if I distribute that negative sign and chase those signs through, we just end up with 2 times what's in the first set of parentheses here. So 512 over 15. We're multiplying that by rho over 2. So our moment about the x-axis after we simplify, because 2 goes into 512 256 times, we get 256 rho over 15. So we have all the integrals that we need to complete. So the moment about the y-axis is mx over m, and that's 256 rho over 15. And we're dividing by the mass, 32 over 3, so that means we're going to multiply by 3 over 32 rho. Notice that the rows cancel. This is all of uniform density, and it'll always be the case when you find the coordinates for the center of mass that those factors of rho cancel. 32 goes into 256 8 times, and 3 goes into 15 5 times, so we get 8 fifths. And so the center of mass is 8 fifths. So going over here on the figure, kind of mark out the y-axis here. 8/5 is like 1.6, so it's like not quite as far as 2. It's definitely less than halfway up. Now that makes sense that the center of mass should be less than halfway up. If we think of the center of mass as, like, if I could cut out that planar lamina and hold it perfectly horizontally, the center of mass tells me, where should I kind of point, place my pencil so it would balance perfectly. And the figure is just sort of wider on the bottom. So I would expect that center of mass to be kind of pulled down in that direction. All right. So, as I mentioned before, the center of mass is always, when you find the center of mass, the factor of rho always cancels when you go and compute, mx over m or my over m. So in a problem where they say just find the center of mass or find the centroid, you could usually just make the assumption that rho is equal to 1. And then you just kind of can leave it out of your formulas. Be careful with what they're asking you to find, though, because if they actually say also to find the moments, if they say find the moment about the x-axis, find the moment about the y-axis, then you really do need to include rho in those. So in example 322, they say find the centroid of this region, bounded by the graphs of f is 4 minus x squared, so the same graph, but now our g of x isn't 0, it's x plus 2. So it does change our region. They say find the centroid. They don't ask us to find the moment, so we'll just assume that rho is equal to 1. So let's sketch this out. I like sketching for these problems because it gives me a way to kind of guess, like where I might expect the center mass. And when I find it, I can see if it makes sense, like that point that I find, does it make sense that that's where the center of mass should be? So there's our 4 minus x squared. And then x plus 2 has a slope of 1 and a y-intercept of 2. And it will look like this. So now the region that we're looking at is this right here. Now, let's see. One of the things, if we're going to do these integrals, we'll need to know the limits of the region. So let's find those first. So let's say x plus 2 is equal to 4 minus x squared. If I gather everything on the left, we'll have x squared plus x minus 2 equals 0. And this will factor plus 2 minus 1, and so that gives us x minus 2, x equals minus 2, or x equals positive 1. The minus 2 seemed pretty clear looking at the figure, and then x equals 1 is up here. Alright, so let's compute our integrals. So we have 3 integrals to compute, one for mass, one for moment about the x-axis, one for the moment about the y-axis. Let's just get started here. The mass is the integral from minus 2 to 1 of f of x minus g of x dx. Again, we're assuming that rho is equal to 1, so I can leave out that factor. Now, in these integral formulas, if we go back, I'm just going to go back to that sheet here. We're going to need the expressions for f minus g and f plus g, so I'm just going to go ahead and do a little side work and find those. So f minus g is 4 minus x squared minus x plus 2, and that is 2 minus x squared. And f plus g, f of x plus g of x, is 4 minus x squared plus x plus 2, and that is 6 plus x minus x squared. Alright, so coming back over here to the mass integral, we're integrating from minus 2 to 1. F minus g is 2 minus x squared with respect to x. That's a nice polynomial. And then we'll plug in our limits. If we plug in 1, we get 2 minus a half minus a third. And then if we plug in negative 2, we get negative 4 minus 2 plus 8 thirds. And let's plug that in. We get 9 halves. All right, so there's one integral down, 2 more to go. The moment about the x-axis is given by the integral of f plus g over 2 times f minus g with respect to x. Again, we're assuming that rho is equal to 1, so I've left that out. I'm going to pull the factor of 1/2 outside the integral. And then we have, let's see, f plus g is 6 plus x minus x squared. And then f minus g is 2 minus x squared. 1/2 times the integral. Oh, and I need my limits from minus 2 to 1. If you multiply that all out, you will get, and you can set up the, the grid or the table, or just, kind of use a bunch of arrows to kind of distribute every factor. But you'll get this expression here, 12 minus 4x minus 9x squared plus x to the 4th. From minus 2 to 1. And now it's a polynomial, so we can integrate. The integration itself is not hard. 12x minus 2x squared minus 3x cubed plus 1/5 x to the 5th from minus 2 to 1. And we'll plug in our limits. So plugging in positive 1 gives us 12 minus 2 minus 3 plus 1/5. And plugging in negative 2 gives us negative 24 minus 8 plus 24 minus 32 over 5. And let's see, 12 minus 2 minus 3 plus 1/5. It's 36 over 5 for the first set of parentheses, and then negative 24 minus 8 plus 24 minus 32 over 5 is a negative 72 fifths, which we're subtracting, so we'll add 72 over 5. Alright, let's put this together. 36 over 5 plus 72 over 5. Half of that is 54 over 5. And there's our moment about the x-axis. Okay, so we've got our mass, we've got our moment about the x, one more integral to compute, and then we'll be ready to find our centroid. So the formula for the moment about the y-axis is x times f minus g. So that's x times 2 minus x squared. Again, we're assuming rho is equal to 1, so I've left that off. I'm going to just distribute that x before we are ready to integrate. Alright, so power rule time. We get x squared minus 1/3 x cubed minus 1/4 x to the 4th from minus 2 to 1. And now we'll plug in our limits. If we plug in 1, we get 1 minus 1/3 minus 1/4. And if we plug in 2, or negative 2, we get positive 4 plus 8/3 minus, let's see, 4. Negative 9/4 for the moment about the y-axis. And now, finally, we're done integrating. Let's put this together, get our centroid. So the x-coordinate is my over m. So negative 9/4, and dividing by the mass means we're going to multiply by the reciprocal, so times 2/9. And that's a negative 1/2. And for the y-coordinate, we're going to take the moment about the x and divide by the mass. So that is 54 over 5 times 2/9. 9 goes into 54 6 times. So that's 12/5. And that means that the centroid has coordinates negative 1/2 and positive 12/5. And positive 12/5, that is 2.4. And I'm bringing that up just because if we want to go up here and see where it's located, negative 1/2, 2.4 is probably right about there. So, this is an example of a problem that would take maybe the most amount of work. Sometimes we could take advantage of symmetry. At worst, you have like 3 whole integrals to do in order to get the center of mass or the centroid. Now, sometimes you might see a problem like this where they want you to find the centroid of some kind of simple region, and by simple I mean kind of simple geometric figures. Here we have one that's sort of just composed of different rectangles. But they're like different regions, right? Like it's not just a smooth continuous function. In fact, this one's not going to take any integration to do, which isn't to say that there aren't some problems like this that might require integration depending on what these different regions look like. But when you have what looks like kind of connected pieces, but these pieces are definitely kind of their own, their own thing, you could just approach it by kind of like the way we did. I'm going to scroll back up here a bit. Kind of like the way we did this one. And because the simple regions that we're looking at, they're all like symmetric regions. And we could kind of break it up into different pieces and just consider all the mass to be located at an isolated point. So what I mean by that is that we could break it up maybe like this and like this. So I could think of it as 3 different pieces. And if I do that, then because they're perfectly symmetric, I can think of the mass of each piece being located right at the center of that piece. So in this way, I could think of it as just a collection of isolated masses, which is more like that first example that we worked out. So I'm going to label these regions here. I'm going to call this region A. I'm going to call this region B. And I'll call this region C. What we don't have right now are any axes, so I'm just going to impose a set of coordinate axes. And I'm just going to put the origin right at the corner there. So now we have the ability to get locations of each of these isolated masses. So for up here in the first region, in region A, let's see, they gave us some distances. So this is an x-coordinate of 1. This middle piece is 3 units long, so there's an x-coordinate of 4. And then the last piece is 2 units long. There's the x-coordinate of 6 at the very end. And that tall piece on the left, region A, is 3 units high. So the center, the midpoint of that rectangle is the midpoint. X is 1/2, and the y-coordinate is 3/2. For region B here, the y-coordinate seems easiest to find first. That'll be a y-coordinate of 1/2, and then the x-coordinate is going to be halfway between 1 and 4. So that's 1 plus 4 is 5/2. And then for this point, the x-coordinate is halfway between 4 and 6, so that's 5. And the y-coordinate halfway up is a y-coordinate of 1. Now the masses of each, if this is a simple plane region of uniform density, the mass is really just the area. So let's find the area of each, which is simple. They're rectangles, right? We don't need to do any integration for this. So this area for region A is 3 by 1, or 3. So we have an area of 3 located at the point 1/2, 3/2. For the B region, this has an area of, let's see, that's also 3, located at the point 5/2, 1/2. And for C, that's an area, that's a 2 by 2, so that's an area of 4, located at the point 5, 1. So for finding the centroid, we need the total mass, but that's just the total area. So we have a total area of 10. And we're going to get the coordinates of the centroid like we did in that first example. So I know I'm going to take the moment about the y and divide it by the total area of 10. And the moment about the y is obtained by taking the mass, or in this case area, times the x coordinate, and then adding each of those up. Now in the numerator, when you do that, you're going to get a total of 29, and then divide that by 10, so we have an x bar of 2.9, and then we'll do the same thing for the y bar. Our total area is 10, so I'm taking each mass now by the y coordinate. When you add these up at the top, you get 10, so y bar is equal to 1. So this centroid is at 2.91.